Hi everyone, in this video tutorial we are going to be talking about configurational isomers. Configurational isomers are isomers that have atoms and or groups attached differently in 3D space, right? But the groups are still attached to the same carbons and the configurations are different, okay? Configurationally we have some difference, okay? So note that configurational isomers can be chiral or achiral. I know I haven't done a video on that yet, but I want to stress that ahead of time. Kind of plant that seed. They can be chiral or achiral, okay? Now, certain types of stereoisomers like enantiomers, those have to be chiral. But when it comes to diastereomers, diastereomers could be chiral or achiral. We're planting that seed ahead of time. Now, the term enantiomer, what that means, enantiomers are non-superimposable mirror image compounds, okay? Now, when you look at enantiomers, they are configurational opposites of each other at every asymmetric center. For instance, these two compounds are enantiomers. There is one asymmetric center. Notice how the left one is S, and in the right structure, it's R. These are non-superimposable mirror images. Here is a mirror plane. And notice how when you draw the mirror image, say of this left compound, this OH is kind of pointing to the right, up and to the right. In the mirror image, it should be pointing up and to the left. It is mirrored over, but the wedges are the same. But what has changed when we've mirrored this over is the relative clockwise counterclockwise, and I've proved that with configurations ahead of time, okay? Compounds that are mirror images of each other and that are non-superimposable are enantiomers, and each compound is in its own right a chiral molecule. In fact, a chiral molecule is defined by saying that it has a non-superimposable mirror image, and that non-superimposable mirror image is its enantiomer, okay? Now, we also have another type of configurational isomer, stereoisomer, which is a diastereomer. This has kind of a more vague definition. A diastereomer is a configurational isomer that is not an enantiomer. Okay, they are not enantiomers, but they're also not identical. Okay, so let's look at an example of a diastereomer. Here you have a compound with a bromine and an ethyl 1,2. They're still 1,2 to each other. And configurationally, notice how the left one is RS and the right structure is SS. So configurationally, the carbon with the bromine has changed. Configurationally, the carbon with the ethyl has stayed the same. Okay? The point here that I want to make is that they are not configurationally opposite like enantiomers would be, and they are not configurationally identical, right? So they're not the same, and they're not complete opposites in configurations. They're somewhere in between. That's in essence what a diastereomer is. It is a configurational isomer that is not an enantiomer. So you could have 100 asymmetric centers in a molecule that are R, and its enantiomer would have 100 S configurations. Okay, they would be complete opposites at every asymmetric center. But an example of a diastereomer might have 87 R and 13 S, or you could have 50 R and 50 S configurations, and that would also be a diastereomer of your reference molecule, which had 100 R asymmetric centers. So diastereomers can have 1 or 2 or 3 or 4 different, but they won't be between each other configurational opposites at each asymmetric center. That would be an enantiomer, and they can't all be the same. Something is different, either 1 or 2 or 3, really depends upon how many asymmetric centers are in the molecule. Okay. Now, we have other types of diastereomers that are achiral, and this includes compounds that are cis-trans isomers and also easy stereoisomers, okay, like this compound and this compound here. They are technically considered diastereomers. Here you have the E isomer, here you have the Z isomer. These are diastereomers, okay? These two compounds are cis-trans isomers. Here we have the cis isomer, here we have the trans isomer. What you will notice, though, is sometimes professors will refer to these cis-trans isomers as geometric isomers, okay? So definitely cater to what your professor is Using as a sub-classification, technically diastereomer is the umbrella term here for these compounds, but you could call cis-trans isomers geometric isomers, and you could call also EZ diastereomers geometric isomers, okay? So just be familiar with that second kind of sub-designation for these types of diastereomers. Why we classify this as geometric and why we wouldn't classify these as geometric is here there's a configurational difference in terms of R and S. We would not call these geometric isomers. If there's R and S, there's chiral carbons that are changing and differing, we're going to say just diastereomer. But if there are no asymmetric centers, but we still have cis-trans isomerism or EZ isomerism, you may see your professor use the term geometric isomers to describe those. These are compounds lacking asymmetric centers, but there's still this isomerism, this stereoisomerism. Okay, so just to recap, enantiomers are non-superimposable mirror images. They might contain chiral carbons, but there are actually instances, we'll get to those later, called atrope isomers. I'm just going to write that down real quick. Atrope isomers, which are compounds that are enantiomers. They are chiral molecules. They are enantiomers that lack asymmetric centers, yet are still chiral. Now, usually, having asymmetric centers can result in there being an enantiomer. That's not always the case. So I want you to think enantiomers, usually if there are configurations, will be configurational opposites. But the true definition of enantiomers is that they are non-superimposable mirror images. Okay? At the end of the day, if a molecule contains asymmetric centers, we can use R and S to our advantage. That's why I stressed R and S so heavily in our intro videos here, because we can use it to our advantage to determine the relationship between two compounds.